Hey everybody, brand new topic on friction. So I know you've seen this in physics class before, so hopefully it's just like an easygoing review. So imagine there's this giant crate, and then you're trying to push it, and it has some mass m. But there's friction between the crate and the ground over here. Okay, so then if we draw the free body diagram, there's normal force from the ground. There's this force that you're applying. I'll just call it force from the person. The crate has weight. And then there's going to be friction opposing the motion over here. I'll call it small f for friction. Okay, so there are two types of friction, depending on if the crate is moving or if it's just sitting there static. So there's static friction. I'll just call it F sub S for static. And then there's kinetic friction. Right, so static friction for when this object is not moving, and then kinetic if it's already moving. And what happens is there is a contact force. So the normal force is the component of the contact force normal to the surface, and friction is the component of this contact force along the surface, parallel to the surface. And what it turns out that the two components of the contact force are just directly proportional to each other. So like this. Friction is proportional to the normal force. Proportional to normal force. So the static friction force is proportional to the normal force. The kinetic friction force is proportional to the normal force. And so the constant of proportionality is called the coefficient of friction. So this is the coefficient of static friction. This is the coefficient of kinetic friction. And right, if this is newtons and this is newtons, the units for the coefficient of friction it's dimensionless. So it'll be a value like 0.1, 0.2, 0.3, something like that. Okay, so let's talk about these one at a time. Let's say the crate is already moving, like it has some velocity here, non-zero velocity. So it's moving. So it's as simple as this. However much normal force you have, whatever the coefficient of kinetic friction is, just those two, multiply those two together, kinetic friction. Static friction has some nuance to it. So imagine you apply 1 Newton of force to the crate toward the right, but then it doesn't move. So let's say pick coordinates here. So some force is in X. We got force by, I'm looking at this free body diagram from the person, minus friction equals mass times acceleration in the X direction. Let's just focus on that. I'll write the Y component. Normal force minus weight equals mass times acceleration. So if there's only motion horizontally, there's no acceleration in the Y direction. So N equals mg, and then the friction is proportional to that normal force. Okay, but let's go through this kind of thought exercise. If you apply 1 Newton of force toward the right, and the crate doesn't move, then the acceleration is 0. So if this is 1 Newton, this is going to be 1 Newton. So you're going to have 1 Newton of friction, static friction, right? Because it's not moving. So 1 Newton of static friction. Now let's increase. So let's say you go 2 Newtons of force toward the right. It still doesn't move. So now 2 Newtons of force still doesn't move. Acceleration is 0. Therefore, the friction is static. So now you have 2 newtons of static friction. And then let's keep going. 3 newtons of force, still doesn't move. 3 newtons of static friction. 4 newtons, 5, 6, 7, 8, 9, still doesn't move. So already we're seeing that static friction is a range of forces. Let me graph it. So let's say this is friction over here. And this is the force by the person. Okay, so already we're seeing a range like this, right? The more force you apply, the more friction there is. But at some point, let's say like 8, 9 newtons, 10.000 newtons, it still doesn't move. But at 10.001 newtons, finally the crate budges and then it starts sliding. So there is a maximum value. So what I wrote here isn't super precise. It should be like this. See, static friction is a range. It's a range of values. The maximum is when it's exactly equal to this. But it can be less, right? Like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if you exceed this maximum value, then it'll start sliding. And the nuance is, even more so, it'll take less force to keep it sliding than it did to get it sliding in the first place. So let's say you go 10 newtons to break it free, but then you only need to apply 8 newtons of force to keep it moving. And you can think about your experience in life, right? Like, it's easier to keep something moving when it's already moving. Once it stops and it gets stuck, it takes more force to get it to move. So typically, the value for the coefficient of kinetic friction is less than the value for static friction, coefficient of static friction. Okay, so you can remember like this picture to remind you of the story. Okay, let's try some practical question. Let's say something straightforward. Like there's a ramp and you put a block over here of some mass m. And here's some angle. So let's say we know, I'll just make up some numbers. So let's say this is 30 degrees. And this is 1 kilogram. Okay, let's say we've already done some experiments and we know that the coefficient of kinetic friction is 0.3. Coefficient of static friction, 0.5. If we put this block on the ramp, is it going to slide? I don't know. I have no idea. If the ramp were like really steep, I'd be pretty confident it'll slide. If the ramp were just like this, like a really small angle, then I would maybe guess it's not going to slide. So something like this, I'm not sure. It's kind of in between. So how do we figure that out? Let's draw the free body diagram. So there's normal force, normal to the ramp, right? It has weight. And then there's friction opposing the motion. I don't know if it's static or if it's kinetic. I'm not sure at this point. So let's use some critical thinking skills. Let me just pick coordinates. And let's sum forces in x and y. So x direction we got mg sine theta minus friction. I'm not sure what kind of friction that is. Y direction and minus mg cosine theta. Okay, so for sure there's no motion in this direction. So ay is for sure 0. Ax, I don't know. It might be 0, it might not be. So here's our critical thinking. Is there enough force in this direction down the ramp to overcome the static friction opposing that motion? So it's like tug of war. Is there more force this way than there is this way? If yes, it'll slide. If not, it won't. So let me phrase the question like this. This is going to be the component of the weight down the ramp. So let me jot that down, mg sine theta, greater than how much static friction can we have at most, static friction max. Right, so if this is true, it'll slide. If not, it's just going to sit there. Okay, so what is this again? That is at most mu s times n. Okay, now let's take a look right here. N minus mg cosine theta equals 0, therefore n equals mg cosine theta. So right here, n, I can just substitute mg cosine theta. Okay, and then we can simplify this a little bit. Mg is non-zero, so I can divide both sides. Why don't I take this cosine and move it over here? Over here. Like that, and I'll move the cosine right here. Okay, and then that's tangent. So I could phrase the question more like, is theta greater than arctangent of mu s? Right, so if the angle is sufficiently large, more than this number, then the block will slide. If not, it's just going to sit there. So let me maybe punch this in the calculator. Okay, so for the numbers I made up, I just said 30 degrees, right? So then arctangent of 30 degrees is 26.6. Oh, no, sorry. Arctangent of 0.5 was the number I made up for static friction. And then our ramp was 30 degrees. Okay, so arctangent of 0.5 is 26.6. And then the angle of the ramp was 30 degrees. Right, so yes, this is true. So then what does that mean? There's more force going down the ramp to overcome the static friction. Okay, so then that means our free body diagram, this should have been kinetic friction. And then the acceleration is non-zero. Okay, and then we'll deal with problems like that next semester in dynamics class. Okay, so that's just an introduction to friction. Now let's talk about how we can use these as supports and how it ties to frames and machines. Okay, so I'll see you on the next video.